In general, do you favor or oppose the busing of black and white school children from one school district to another?
In general, I would favor it.
Social scientists at the National Opinion Research Center want to know how the opinions of Americans are changing over time. To find out, each year they interview 1,500 people who represent the entire population.
Hi, I'm Miss Cheatham from NORC at the University of Chicago.
The sample is chosen at random, so that if the poll were repeated, the accidents of chance would choose different people, which would no doubt yield a different poll result. A medical experiment wants to test the effect of aspirin on heart disease. Subjects are assigned at random to one of two groups: those who are in the treatment group and take aspirin, and those in the control group who take a placebo. Again, different assignments would yield a different experimental result. Manufacturers, too, use random sampling to test whether products meet specifications. Whether the sample is people or potato chips, we could expect that independent random samples will lead to different results. If this is so, how can we ever trust what we learn from random samples? We'll be looking at this problem of variability in this unit. We'll see that when we take random samples, the variation follows a regular pattern. We call this regular pattern a sampling distribution. The sampling distributions we'll focus on are the familiar normal distributions. We'll look in detail at the distribution of an important sample statistic, the sample mean X bar. We'll look at applications of X bar in manufacturing, where control charts are used to monitor product quality. And finally, we'll introduce the central limit theorem to demonstrate the importance of normal distributions in statistics. This AT&T plant in Oklahoma City is highly automated. A robot makes a delivery run, then returns to plug itself in when its battery runs low. The product made here is high-tech also. The complex electronic circuit boards that enable callers everywhere to reach one another. Each board has 2,000 electrical connections on its underside. They're all soldered at once by passing the boards through a standing wave of molten solder. If things go wrong, like if the temperature of the solder or the speed of the conveyor isn't right, then the connections on the boards will be faulty. And if these connections aren't made well, then the connections between callers won't happen either. So AT&T has to make sure that the circuits are soldered properly. And they can't wait until the end of the line to uncover problems in the system. So at key points along the way, a worker randomly selects 5 boards to inspect carefully. Each board is scored for the quality of the solder joints. 100 is the standard. A score of above 100 is above the standard, and below 100 means that the board fell short of the target. If the average score of the sample is too low, the wave soldering machine will be adjusted right away, so problems are caught before they become serious, before they show up in finished boards of poor quality. This is called statistical process control, looking regularly at samples of a few items in order to catch problems when they occur, instead of letting them compound by waiting.
If we looked at 100% of the product, it would take more time, more people, and would not give us any better information about the process. There was a time when industry thought that a quality control department's function was to inspect quality at the end of the line. Now we know that the only reasonable philosophy is to build it right the first time.
While the average quality score of the circuit boards is 100, some individual boards will have higher scores and some will have lower scores. AT&T expects this variation. It's natural in any process. When everything is working right, the variation in the circuit boards is described by a normal distribution. The mean of the normal distribution for the population of all boards is 100. That's the average score we would see if the process ran on forever in its proper state. The standard deviation of the population of quality scores is 4. The problem is, sometimes the process doesn't run like it's supposed to. To see if it needs adjusting, AT&T takes an average of the scores of its sample of 5 boards. This average score is the sample statistic, the sample mean X bar. Because the boards aren't all the same, the average score X bar will vary depending on the luck of the draw. Let's see what happens if we keep taking samples and calculating the mean score X bar. We'll take repeated samples of 5 circuit boards and record the average quality for each sample. Here's the quality scores for our first sample. The average is 99.4. In a second sample, we get a different 5 boards and a different average, 101.6. Another sample, another average, this time 99.9. We keep on sampling 5 boards and calculating their mean score X bar. What we're doing is accumulating data, the values of X bar. We want to know the distribution of these values. The distribution of values that X bar takes when we sample repeatedly is called the sampling distribution of X bar. We've looked at the distribution of individual observations before. What we're looking at here is the distribution of averages. The first thing we notice is that there's variation. The averages aren't all the same. But as we take more and more samples, a pattern begins to emerge. It's a normal distribution. Here's the first big fact about the sampling distribution of a sample mean. When the population is normal, the sampling distribution of X bar is also normal. Now, what's the mean of this new distribution? It's 100, the same as the mean of the population. Even though some samples have scores above 100 and some below, in the long run, the center of the distribution is the same as it is for the entire population. If the mean of the population were to change, the center of the sampling distribution would move to the new population mean. We use the sample mean X bar to estimate the unknown population mean. In statistical language, we've just seen that X bar has no bias as an estimator of mu. Individual samples may give an X bar above mu or below mu, but the distribution of X bar is centered right at mu. Let's compare the sampling distribution of X bar with the distribution of individual observations. Both have the same center at mu, the mean for the population. But the distribution of X bar is taller and skinnier. That is, this normal curve has a smaller standard deviation. You might have guessed that averages of several observations are less variable than a single observation. In fact, there's a precise relationship between the standard deviation of the distribution of sample means and the standard deviation of the population. We'll call the standard deviation of the distribution of sample means sigma sub X bar. Here's the formula. Now we have 2 more big facts about the sampling distribution of X bar. The mean equals that of the population, and the standard deviation is that of the population divided by the square root of the sample size. Larger samples concentrate X bar closer to mu. But that square root means in order to cut the standard deviation of X bar in half, we'd need a sample size 4 times as large. The point of all this is that large samples give more precise results than small samples. If you start with a sample size of, say, 200 and go up to 1,500, you can see that the distribution of X bar becomes ever more concentrated as the sample size gets larger. So a sample mean from a large sample is likely to be very close to mu, which makes it a good estimate. The behavior of the sample mean, as described by its sampling distribution, lies behind a basic tool of statistical process control, the X bar control chart. An inspector enters the mean quality score for each sample on a chart plotted against time. That's always the first thing to do. Plot your data. As we might expect, we see variation. What we need to do is distinguish the chance variation that is part of any process from the extra variation that shows that the process has been disturbed. The sampling distribution lets us compare the data with what we expect to see. Here's the normal distribution of x bar. If the process has not been disturbed, the mean of the x bars will be here at 100. So we draw a center line at this mean. Now recall the 68, 95, 99.7 rule for any normal distribution. Almost all observations, 99.7 to be exact, will lie within 3 standard deviations on either side of the mean. Now we've learned that the standard deviation of x bar is that of the population divided by the square root of the sample size. In this case, it's 4 divided by the square root of 5, or 1.79. So to go out 3 standard deviations from the mean, you would multiply 1.79 times 3, and both add and subtract that product from the mean. The dotted lines at 94.63 and 105.37 represent what are known as control limits. As long as the quality scores remain normally distributed with mean 100 and standard deviation 4, that is, as long as the wave soldering process continues its past pattern, almost all of the x bar points on the chart will fall between the control limits. We say the process is in control when its pattern of variation is stable over time. A point outside the limit is evidence that the process has become more variable, that it's gone out of control. As soon as an inspector sees a point like this, it's a signal to find out what's gone wrong. Statistical process control is based on quite small samples taken at regular time intervals.
Yes. Good morning. My name is Terry Hansen. I'm from the United States Census Bureau. The Bureau is conducting a survey of employment and unemployment here and across the nation. I have some questions to ask you. Did you receive our letter?
Yes, I did.
Many statistical studies, such as the one the Census Bureau conducts for the Bureau of Labor Statistics, use much larger samples.
What were you doing most of last week? Working or something else?
Working.
How many hours did you work last week at all jobs?
I worked 3 days, about 24.
The Census Bureau interviews a sample of 60,000 people every month to find out things like how many people are employed and what is the average income of American households. Now, the distribution of household income is not at all normal. It's strongly skewed to the right. There are many moderate incomes and a few very high ones. So the distribution of the sample means for incomes that would emerge if we took repeated samples isn't exactly normal. Here, for example, is the distribution of average income x bar for random samples of 4 households. It's still skewed to the right, but much less so than the distribution of individual household incomes. And here's the sampling distribution of x bar for samples of 10 households. This curve is still more symmetric. In fact, its shape looks roughly normal. A truly remarkable fact is starting to emerge. No matter what the distribution of individual observations looks like, the distribution of the average x bar becomes more and more normal as we average over large samples. For really big samples, like the 60,000 households that the Census Bureau interviews, the distribution of x bar will be extremely close to normal. This remarkable fact is called the central limit theorem. It says that the distribution of x bar is close to normal when the sample size is large. In this unit, we've discovered that the variation in sample means follows predictable patterns, depending on the characteristics of the population they're drawn from and the size of the sample. The pattern is described by 3 big facts about the behavior of sample means. When the population is normal, the sampling distribution of x bar is also normal. The mean equals that of the population, and the standard deviation is that of the population divided by the square root of the sample size. And when n is large, x bar is close to normal, even if the population is not normal. With these facts in hand, We're now ready to do the most challenging and rewarding work in statistics: inference, the art of drawing trustworthy conclusions from data.